Good morning, everyone. So this is our fourth class of organic revision of uh, second phase. We have completed the basic IUPAC nomenclature. Today, we have to complete the nomenclature of benzene and its similar compounds. This particular topic, that is benzene and the similar compounds, have considerable importance in the current scenario of how the questions have been asked in IIT JEE. If you carefully observe the type of questions which have been asked since 2007 and onwards, you'll find that the aliphatic compound standard IUPAC nomenclature is missing. And instead, the IUPAC nomenclature of benzene and its derivative has been relatively more given preference or priority in making question papers. So let us start the benzene and its nomenclature. After completing that, we'll move to a very important but usually neglected by the students, the topic called purification of organic compounds. So we'll do that, but first we need to complete our IUPAC nomenclature of benzene and its compounds. The benzene and its relative compounds nomenclature is slightly, I would say tedious, is slightly difficult, or I would say different. And why is it different is because in aliphatic nomenclature, you have to start everything from the scratch. You count the parent chain, you give the number, everything. But here, some of the common names have been as such in continuation been allowed by the IUPAC to be used as such. So let's see how and when they are allowed. First and foremost, if you see, the benzene itself is not an IUPAC name, but IUPAC has allowed the use of benzene as such. We can use the word benzene directly, no need to go for any triene or cyclohex and all those type of thing. It is directly allowed as benzene. Okay, benzene could, in your questions, it could be written as one of the resonating structures, or it could be presented, which is the best way to present the benzene, is as one of the hybrid. So in any which way it has been posed to you in a questionnaire, please follow that it continue to have a name benzene. This is the basic benzene. If I move to mono-substituted benzene, then the compounds obtained, we call them as a benzene derivatives. If there is only one substitution, then we call it mono-substituted benzene. If there are two H from the benzene replaced by some other group, then it is called di-substituted benzene. If three, then we'll call it tri-substituted benzene, and so on. Correct? So, for example, let us start with the word mono-substituted benzene. Now, in case of mono-substituted benzene, first let me introduce to the words or to the names which have been directly allowed by IUPAC. Let's have few examples in this series. For example, CH3. Yes, by IUPAC nomenclature, we can very well call it as a derivative of benzene as methyl benzene. But it has also been equally accepted by the name toluene. Same way, if I write OH, it has been named as benzenol or hydroxybenzene. But it is more frequently seen as the word phenol. Correct? Like this, we have CHO. So it has been given the name benzaldehyde. Okay, but it is, you can call it, of course, by our original special suffix method as benzene carbaldehyde. If I go further in the series, I have so many examples, but some which are important, I cannot neglect them. Like this one, it is commonly, you can call it aminobenzene by the standard rules, but it has been very well accepted as aniline. You can call this compound, okay, this is methoxybenzene. It is also called anisole. Now you see there is a change. There is a change in the word. There is benzene in one, and there is total absence of the word benzene as a closing word, as a closing name in the other commonly accepted names, which IUPAC has allowed as IUPAC nomenclature. Okay, but you should not get confused that if I have this molecule and I name it as nitrobenzene. Now here it is as good as we give by the common methods or the rules that we have studied for aliphatic. It is the same way. There is no change. There is no different name like toluene or phenol or benzaldehyde or aniline or anisole and so on. So there is no special name. It is a common rule-wise IUPAC name given for this compound. Similarly, if I write this, there is no specific name. It is simply chlorobenzene. And when it is chlorobenzene, no particular change in a name as I have said in previously, some new word has not been coined. It is normal nomenclature. Correct? So let us now move to if there is a di-substituted benzene. Di-substituted benzene, it means that now the formula will be C6H4 group 1, group 2, where the two groups could be same or could be different. G1, G2 could be same or it could be different. That doesn't have any impact. They are still called di-substituted benzene. So let us go through them, but before that, let me tell you that in trivial nomenclature, in common nomenclature, that there are certain words which are used for di-substituted benzenes, and they are ortho, position 1, 2, meta for position 1, 3, and para for position 1, 4. But mind it, it is in trivial nomenclature. For IUPAC, you again have to use the proper number 1, 2, 1, 3, 1, 4. So what did I say? Let me exemplify. For example, if I have similar substitution, these two CH3s. So as per my common nomenclature, this is called orthoxylene. But for IUPAC nomenclature, it is called 1,2 dimethyl benzene. See how for IUPAC the word ortho is not allowed and 1, 2 is taken into consideration. Similarly, if I have CH3 at these positions, then I will call it 1,3 dimethyl benzene. And of course, metaxylene. Similarly, a paraxylene will be formed, which will be IUPAC named as 1,4 dimethyl benzene. Okay. Some other similar examples for the purpose is this. Common name. Its common name is to be remembered is catechol. If meta, then it is called resorcinol. parahydroquinol, or simply even quinol it is called. Okay. If I want to go for IUPAC, it is 1,2 dihydroxybenzene, 1,3 dihydroxybenzene and 1,4 dihydroxybenzene. But if the groups are different, this set of examples were when the groups were same. If the groups were different, now different in what sense? Let me say if I have a molecule with CH3 here, okay, and Cl and Cl here. Now I can have, as per our lowest locant rule, I will call it 1-chloro 3-methyl benzene, or I could also call it as a derivative of toluene. I can also name it as a derivative of toluene, and when I call it as a derivative of toluene, please note this point that when you name a particular compound as a derived structure from some base compound or some base name, then the group of that base compound, irrespective of the locant rule or any other preferred functional group rule, is given position number 1. Okay, so here this CH3, because I am going to use the base name toluene, so CH3 has to be at position number 1. So if CH3 is at position number 1, then using this type of nomenclature, this compound will be named as 3-chlorotoluene. I hope now I'm making my point of view absolutely clear that if you are using the word toluene, then it is a base compound you are referring to is a toluene. With respect to toluene, this chlorine is at position number 3. So we are calling it as 3-chlorotoluene. Correct? Whereas when in the first, no base compound, we are directly taking it as a derived structure of benzene. And when we are considering it as a derived structure of benzene, then the common locant, then alphabetizing, all things are being considered as per our usual IUPAC nomenclature rules, and then we have given the name required. Okay, let me take few more example in the series. For example, if I have a compound OH and say NO2. So here I will take phenol as my base compound. Okay, I'll take phenol as my base compound, and so the name is going to be 4-nitrophenol. Okay, and so on. This is the process that is to be there, but you have to remember that the base name has to have some difference from the derived basic benzene names. Okay, otherwise by error you can consider both same and will make certain errors. Don't do that. Okay, on di-substituted benzene, this one question appeared in J 2017. 2017 is not far away for us. We are preparing for 2020 and 2021. So just 3-4 years back, this question, as I told you that these days aromatic systems are being asked, this particular question was asked. Now see, there are both options, the benzene ones and the toluene ones. Okay, and it was a multi-correct, as you can see, is or are. Right, so if I use toluene, so this will become 1 and chlorine will become 4. So B will then be part of the answer. Right, if I use no, I don't want to use toluene, I want to go for the basic benzene system, then by the lowest locant and then alphabetizing rules, I will say 1-chloro 4-methyl, 1-chloro 4-methyl. Okay, so A is also a part of answer. A and B were the answers. This cannot be the answer because this is wrong. 1-methyl 4-chloro. Alphabetizing is done wrong. C should be preferred over M when the set of name was coming identical. Okay, so this is just one example. In my limited time I could take was this one, right? Let us move now to try substituted systems. So try substituted systems, again same thing. Try substituted benzenes. Okay, in first and most important thing, in case of tri-substituted benzenes, we are not allowed to use the terms ortho, meta, para. All these terms are limited only to di-substituted names. For tri-substituted and further, we are not allowed to use these names. We have to go for our basic look and rule, the positioning. That is what we will use. And yes, we can use the base names. That is allowed. That we can take. So let us move to our examples. Let me take my first example of a tri-substituted series is NO2, Cl, and CH3. Correct? So it can have two names. First, 1, 2, 3, 4. So this is 2, this is 1, and this is 4. Correct? This is 4th. If it is so, my name here will be, if I take it as a derivative of toluene, it will be called 2-chloro 4-nitro-toluene. If I don't want to take it as a toluene derivative and want to take it as a fundamental benzene derivative only, then my name will be, then I will call it 2-chloro, right? Now I want to put methyl, 1-methyl. And between methyl and nitro, definitely M will be the preferred letters. So first I'll put methyl, then I will write nitro. So 1-methyl 4-nitro-benzene. 2-chloro 1-methyl 4-nitro-benzene is the word. I hope you are getting my point. Here it is benzene. Nitrobenzene is not a base word. Nitrobenzene is like a, nitro is a prefix. It has got no suffix and no special name has been assigned to it. So it is the usual name given, no special change, whereas toluene, okay, is a different base name. Moving to next example in the similar way. Example number 2 is, if I have OMe, Cl, and CH3. Okay, so now I can call it as either a derivative of any sol or a complete non-base name benzene derivative IUPAC nomenclature. So let me name it both way. First, anisole. So if I use anisole, I will name it as 2-chloro 4-methyl, okay, 2-chloro 4-methyl anisole, or it could be named as 2-chloro 1-methoxy. As per dictionary order, methoxy will be preferred over methyl. Okay, 4-methyl benzene. All right, I hope you are very well Comfortable with what I'm saying now? Let us move to similar example number 3. See, if I have CN, COOH and OH. Correct? CN, COH and OH. So now I will prefer, if given a choice, if it is a single correct, COH is a much preferred functional group. So just if I'm given a choice, I'll prefer it as 1, 2, 5. So I'll name it as 2-cyano 5-hydroxy. Either I will call it as benzoic acid or benzene carboxylic acid. 2-cyano 5-hydroxy benzene carboxylic acid is the name I'll prefer. If it is a single correct, I'll prefer this. If it is a multi-correct and some options are there, then we'll think about more. Moving to similar example number 4. My next example is OH, bromine and chlorine. So now I will have a base nomenclature as phenol. Right? Now either I can go clockwise or I can go anti-clockwise, but to maintain bromine at a lower locant, I will prefer clockwise orientation, and the name is 2-bromo 6-chlorophenol. 2-bromo 6-chlorophenol. Right? If none is to be taken as a base, if there is no chance, there is no probability, whatever given is a derived nomenclature, then how to use it and how to name it? By using the normal locant rule. Let me give you an example. NO2 F C2H5. If this was CH3, I could have used the word toluene, but if it is C2H5, there is no particular word. I cannot use the term what? Toluene. Or any such special word is also not coined for ethyl benzene. So all of them are now normal substituents, no special word. So as per the lowest locant rule, I have to name it as, in alphabetical order, this should be mentioned first. So I have to write it as 4-ethyl. Correct? Now between fluoro and nitro, it is going to be fluoro. The 1-fluoro 2-nitro benzene. Okay, 4-ethyl 1-fluoro 2-nitro benzene. I hope I have made my point clear, but always remember, if any side chain in a benzene name is having the important functional group, is having the preferred functional group, then we don't have to choose. We have to give that side chain as a main parent chain, not the aromatic one. What am I saying? I want to say, if I have a compound like CH2COOH and on this I am given OH. So COH is the preferred functional group. I can't do anything. I have to name it as, okay, I have to name it as parent 2. On 2 I have hydroxyphenyl. But that phenyl is at which position? Hydroxy is at which position? So I'll place like a complex substance that at position 2, I have 3-hydroxyphenyl ethanoic acid. Okay. One last example in this series, which is important, is, let me tell you the name of this compound. If the side chain has more than one functional group, bromine is here regarded as a functional group. And phenyl here is a substance. It is having no preferred functional group. So this is 1, 2, 3, 4, 5. 2, 3 dibromo 1 phenyl pentane. Okay, this 2, 3 dibromo 1 phenyl pentane. That brings us to the closure of IUPAC nomenclature, as concise and as to the point as we can discuss in our current scenario. Now we are starting a very important topic called purification of organic compounds. Purification of organic compounds. Some of you might be really puzzled that what do I have to do with purification of organic compound? Why should I read? Already so many reactions and these things were there. Now they are adding purification also, and not only adding in the theory. In fact, they are asking the questions also on purification. Mains 2019, you have seen there were questions. In 2020, there were questions. Right? This year, there were beautiful questions on distillation and chromatography. This year, I meant 2020. In 2019, there was a question on chromatography. Distillation and chromatography, these two are favorites. Besides this, there are some combinations of purification and reactions that you will learn over a period of syllabus. Correct? So moving to this, why do we need purification? So children, let us be very clear that organic chemistry is not just about writing reactions on the paper, drawing colorful arrows and structures and naming few compounds. No, not at all. Organic chemistry is influencing our life, is influencing our life quality, health quality on day-to-day, on moment-to-moment basis. You might be puzzling that what the madam is saying, how could this be possible? Well, let me take the present scenario. In this corona pandemic condition, you might be hearing or reading in the news continuously that the vaccine is in progress. There is no medical support we are having at this point of time, but our medical scientists, our research scientists are working day in and out to prepare something. What that something is some sort of medicine, is drug, is a vaccine. They are working on that. So if you see all the possible drugs, all the possible medicines that we depend on, starting with aspirin to Iodex to move to paracetamol to cough syrups to cancer medicines to AIDS medicines and whatnot, that complete stream is based on organic chemistry. Preparation of those medicines, their application, their effect of body. So when organic chemistry works hand in hand with other streams of science, be it biology, be it be some biochemistry, then a beautiful outcome that influences a full human race, a complete human species, is the actual application, is the actual outcome of the science that you are being taught in these classes. So please do not look down upon this topic, purification of organic compound, because industrially, commercially, and our health-wise, this is a very important topic. We have seen people taking the drugs over the counter. See, one of the very commonly used drug is aspirin. Just imagine if the aspirin they consider as a one tablet. If they have a headache or something, they just pop in one tablet and become happy. They feel the pain is gone. If that is not pure, what could have had happened? I'm using a very mild example, but otherwise the purification of that drug is so important that it is actually what a person is thinking it is. Correct? So purification is important in our day-to-day life. There are different methods of organic compounds purification. Why we need different methods? Because organic compounds are so different. They could be liquid, they could be gas, they could be solids, they could be soft waxy solid, they could be relatively harder solids. They could have a specific melting point, they could melt, they could decompose before melting and whatnot. They are soluble in something, they are insoluble in other thing. Basis on such a large spectrum of their chemical behavior, of their properties, we cannot purify them by one method. We need so many methods to support or to purify them as per their own nature and our requirement. And that is why there are 5 methods of purification of organic compounds, and all of them are very important. They are all commercially used. I could have found some distillation and all these pictures from the industry that I'll show you in the later part of my lecture, so that you could feel that it is something which is practically applied. So what are the 5 methods of purification of organic compounds? First is sublimation, crystallization, distillation, differential extraction, chromatography. Okay. First and foremost, we'll start from the word sublimation. Correct? Sublimation. And sublimation is a particular phenomena in which there is conversion of substance from solid to gas without passing through liquid state. Then I was telling there are certain examples that we come across in daily life. Of course, iodine is not something that we come across daily life. Dry CO2. Dry CO2, where do you see? In certain, I would say, get-together parties or movies, they have that foggy environment. No? Foggy environment created. That foggy environment created is with the help of dry CO2. Okay. Iodine solid, I don't think that you might have come across in daily life. Naphthalene, yes. Naphthalene is used as a solid balls when we store our books or our old clothes, or we preserve our clothes. Camphor is the one which is used in puja. In Hindi, it is called kapoor. You might have been seen this very frequently as it gets volatiles off so easily. Correct? So how do we use this whole thing? We were discussing how this whole thing is working. So the apparatus for sublimation is somewhat like this. This is our burner. Okay, this is our stand, tripod stand. On that tripod stand, one gauge is placed. Gauge is nothing but a net of iron. Okay, very layman language I'm saying that it is nothing but a net of iron. This is our china dish. China dish, again in a layman language, I'll say is a bowl of ceramic, but with a very high survival. It can sustain very high temperatures. In this, we keep our compound, which is having impurity. So say red is our compound. Okay, and randomly say greens are the impurities in this. Now what happens in sublimation is we heat it strongly. As and when we start heating it, okay, as and when we start heating it, the vapors will move up. Vapors will come to this inverted funnel, right? You take this inverted funnel first to close it from the top. They should not be allowed to move out. So our funnel is closed from the top, and these vapors are collecting in this funnel. Okay, then we close our burner, let this whole apparatus cool. Okay, let this whole apparatus cool. And when we cool, again, sublimation is a reversible phenomena. All phase change things are reversible phenomena. So when we increase the temperature, our substance transferred from solid state to gas state. On heating, when I cool it, it again changes to solid. Okay, it again changes to solid. And thus, on the walls of this funnel, you will see a deposition of solid particles, that is the sublimate, right? The non-volatile, or I would say which could not sublime, such impurities are left in this china dish. Okay, this technique is particularly used only when we have to separate a mixture or an impure compound in which one is sublimable, in which the compound is sublimable, and say impurities are non-sublimable, then you can use it. A very basic example that I can say is, say you all must be comfortable and know the word sand. If I mix sand with powder of camphor, if we mix sand with powder of camphor, okay, we'll crush the camphor and we'll mix here and sand. Now this is non-sublimable. Sand is non-sublimable. But camphor, as I have already told, is sublimable. I'll put it here, allow it to get sublime, allow it to, here is camphor. And then we'll let this funnel cool. When it will get properly cooled, then you will have on the walls of this camphor. Okay, I hope my example is clear. This is how we use sublimation. Next, we come to crystallization. Now, what is crystallization? Crystallization is basically when crystals are formed from solutions. If something is in a dissolved state, if something is already dissolved, and then from there, from dissolved state, when we are changing the temperature, if it forms crystals, solid crystals, then this particular process is called crystallization. Okay, this particular thing is called crystallization. So what is the fundamental that we use for crystallization? We use that the difference in solubility of compound and the impurities in a particular solvent should be sufficient enough. What do I want to say? That both the impurity and the targeted compound is not having same solubility in the particular solvent. They should be considerably different soluble. Okay, so there should be difference in solubility. And for that, we need to find a suitable solvent, because it is not that in all solvents they'll follow this particular condition. So we have to find a suitable solvent in which there will be difference in solubility of impurities and the compound. Okay. Second principle that we use parallelly is that the amount of solute which can be dissolved in a particular solvent increases with increase in temperature. As we heat our compound, as we heat our impure compound when dissolved, then there should be difference in their solubility with varied temperatures. There has to be the difference. If it is not, then we cannot use our method of separation based on crystallization. Okay, so there has to be difference in their solubility in a particular solvent with temperature. That is our second thing that we'll be using. So how we'll do that? Now here I'm saying solvent. As I said, you need to find a very specific type of solvent right? So very specific type of solvent. How to use that? Let me read it out to you. Choosing an appropriate solvent is the important process of crystallization, as crystallization works only when a proper solvent is used. It is important to choose a solvent that will not dissolve the substance at room temperature, the second line that we used. But as the temperature of solvent increases, the solubility of the solute also increases. Okay, at the same time, the impurities that are present must either be soluble in the solvent at room temperature or must be insoluble in the solvent at high temperature. When we decide a solvent, we should take care of the fact that at room temperature, if I take room temperature, if I say my water is just an example as a water, so say blue is water, and this green and red or orange and green are impurities and the compound, then what care I must take? That at room temperature, solute that we are targeting to pure should be insoluble. It should not be soluble, it should be insoluble. Okay, but at high temperature, solute should be soluble and there should be increase in its solubility with increase in temperature. At room temperature, impurities should be soluble. Rather, instead of should, can be soluble. If they are, then okay. If they're insoluble, then also okay. Can be soluble. And at increased temperature, impurities must be insoluble. Must be insoluble. Okay? Correct? So how we'll proceed? What we do? We take a flask. Okay? We put the suitable solvent in that. Whatever. Now we pour our impure compound. This impure compound has both the impurities, let these be black, and the compound we want to purify, let this be red. We always take heated solvent. We always start with heated solvent. We put a glass rod in this. This is our glass rod. We stir it well. We are continuous stirring is done. We want to prepare a fully saturated solution of our compound. We keep on adding our compound till we get small solid deposition on our glass rod. We stir it well, we heat it, and till the time it is soluble, we keep on dissolving. We want to make continuous stirring, say concentrated solution. We make concentrated solution. Okay, we make concentrated solution by this method. Now by doing all this, now we'll put off the burner, and let it cool. We'll put off the burner and let our whole solution cool. Okay, if there is any impurity, which is giving color, then we use charcoal, which will adsorb colored impurities. So you can see sometimes charcoal powder is added or activated charcoal is there. Its function is to adsorb the impurities which are giving color. Okay, so when you let it cool, then again solid compound will start coming out of solution. This is pure. This is pure compound. Of course, it is not 100% pure. You have to repeat this whole thing, repeat the process, repeat the process 2-3 times. Okay, repeat the process 2-3 times. That will help us to improve the percentage purity of our compound. Okay, so I like an example. This crystallization or recrystallization is a very important method for purification when we prepared in lab. See, this is a recrystallized benzoic acid. This is how benzoic acid looks when we recrystallize it from the solution. Okay, see the steps. This is a hot solution. Okay, in that benzoic acid solution, they are further adding solvent which is hot. That is why they are holding with this type of clamp. Take continuously adding charcoal, because as you can see there is color. Okay, so then benzoic acid solution is not colored. So to remove this color, see, this is charcoal. They are adding charcoal. ये solution के अंदर you can see there is black. Okay, when this is done, then by gravity separation method, this is filtered and separated. Charcoal is separated. Okay, so after separation of charcoal, the solution becomes colorless, and then you let it cool. This filtration is in hot condition, huh? This is done in hot condition, and then you let it cool and filter. You will see this shiny crystal like appearance. This is of recrystallized benzoic acid. Okay, you can separate so many things by crystallization, but this is just, I wanted to have a real feel that how actually things work in lab. This is how it will work. Okay, you can use this method for other examples also, for other impurity related things also. For example, we can have a sugar and common salt. If they are mixed, then by the use of ethanol, this is the mixture and this is the solvent that should be used. You can separate them. You can separate sugar and common salt by the use of solvent. Solvent, as I have already told, is a very important criteria. So I am referring to the solvent always. Let me give you second example. Phthalic acid and naphthalene. Okay, if you want to separate this, then use hot water. Phthalic acid is soluble in hot water. If you use hot water, you will have the point of difference. Okay, I think you can understand. If you have, say, potash alum, potash alum and say benzoic acid, again you can use hot water. Benzoic acid is soluble in hot water, insoluble in cold. Potash alum is soluble, highly soluble, I would say, in cold water also. Okay, you can have a blue vitriol, that is copper sulfate separation, by adding acidic water, and so on. So there are so many methods, so many combination of impurities that you can remove using crystallization. Okay, now as crystallization, we have just said, is based on solubility. Sometimes we may come across that both impurity and the compound we want to separate have very close solubility. Okay, if there is a very similar solubility of the two compounds in a particular solvent, then we will go for fractional crystallization. Take. So we want to say impurities and solute both are soluble in a particular solvent, there is close solubility difference. We will have hot saturated solution of the mixture. Okay, we'll prepare hot saturated solution of the mixture. This should be hot. Okay, this should be whichever solvent we are using uske andar, inside that whichever solvent we are asked to use, in that we have dissolved, correct? And then we'll allow it to cool. Then allow it to cool. Some solid will separate. Then again repeat, and then again repeat. A series of repeated crystallization will ultimately separate the two compounds, say A and B, but only when you'll repeat this step again and again and again, then only you will have a separation of the two compounds. Okay, so that is fractional crystallization. Now let us come to the most important, I would say, this and chromatography, distillation and chromatography. So one of the most important is distillation. It is the most important for separation of our organic liquids. It is very important. It is used for organic liquids. The two steps that we use in distillation in general, the two steps that we use in distillation in general, first is vaporization. And step number 2 is condensation. First, we vaporize our liquid to gas phase, and then we condense those vapors back to liquid state. Okay, so what is the criteria? Why, on what basis this distillation is defined? What is the criteria? Okay, so it is used, the primary condition that we want is, it is used when, okay, it is used when there is a volatile liquid from non-volatile impurities. If the impurities are non-volatile and we have to separate volatile liquid from that, then you can use distillation. Or I can say you can have two liquids. One is the impurities are totally non-volatile. Other is, okay, the impurity is also a liquid and our targeted liquid substance is also liquid. But the liquids which we are having have sufficient difference in their boiling point. Okay, they should have a sufficient difference in their boiling points. So what is this sufficient? Usually it is somewhere 20 to 25 degrees centigrade difference has to be there in the two liquids which can be separated by normal distillation. If it is less than this, then we cannot separate it by this method. So how will we separate? See the apparatus of distillation. Okay, apparatus of distillation. What is there? This is the burner. Okay, RB flask is the round bottom flask. This is round bottom flask. They have very long neck. In this, the impure liquid is heated. As we have already told, distillation is used for impure liquids. Now it is heated. So when we'll heat, then gases will start forming. Okay, here is the temperature that is that is used to maintain the temperature of the condition, so that yes, the boiling point of a particular liquid could be achieved. Okay, we'll heat till its boiling point, then it will start moving up like this. And then here we are taking it out of this particular compartment, and see it is being taken from this long pipe to a different flask. Okay, here it is vaporization, and from here it is coming, it is undergoing condensation. How condensation? Here is a cold water inlet. It is a jacketed arrangement. If you can see, the inside pipe is surrounded by a jacket. That jacket has a cold water. Here it is being introduced inlet, and from here that cold water is removed continuously because it will absorb heat. Now it will become hot. So it is removed. It is cold and can be recycled. But yes, it is removed. So that water, cold water, condense the gas which is coming into liquid. And from here, see droplets. Droplets are droplets of liquids are being collected here in a conical flask. Okay, this is our pure liquid. I am not saying it is going to be 100%. You might have to repeat the steps again and again. But this is how we do. Now we need to have at least a 25 degree centigrade difference. Otherwise, vapors of both the liquids may come. So that is why we said there should be at least 25 degree difference, and we can use this method very easily, and it is in fact used very commonly. Okay, let me tell you some examples where this method is used. We can separate chloroform, which has a boiling point of 334 Kelvin, when it is mixed with aniline, which has a boiling point of 457 Kelvin. So if you see, there is a difference of 123 degrees between the two. We were just thinking at least 20-25 ho, but here it is 123 degrees difference. So it is very good combination for us to use for the separation of chloroform and aniline. Example number 2 is we can have separation of benzene. BP is 80 degrees centigrade, and when it is mixed with aniline. So aniline you already saw is so high. If I want to say in degrees centigrade, it is 184. Okay, you can separate ether, which has boiling point of 35 degrees centigrade, when it is mixed with toluene, which is having a BP of 110 degrees centigrade. Okay, and so on. So this is a very common method. The only criteria we need is a considerable difference in their boiling points. We can use this. Okay, here I have put the same note again, that useful when the boiling point of liquid in the mixture differ by at least 25 degree centigrade. This is a thumb rule. It is not a fixed anywhere written. It is a thumb rule that we use. Next we come to the term fractional distillation. Now what is fractional distillation? Fractional distillation is used, okay, when the two liquids, okay, when the two liquids both volatile, take, and have close boiling point to each other. Two liquids have close boiling point to each other, then we will use fractional distillation. This is very important topic. This is very important topic. Fractional distillation we use when both the liquids, okay, have very close, I would say less than 25 degrees centigrade in general. Then we use fractional distillation. Correct? Why the word fractional distillation is there and all that thing, I'll discuss. I'm coming to that point, that why this term is there. So what actually happens, see, if you'll compare this fractional distillation apparatus and the normal apparatus, the only difference you will see is this column. See, it was same. The round bottom flask, the liquid is kept, it is being heated, the thermometer is there, it will come to gaseous state. See the condenser, same process, the water inlet, the water outlet. And here the adapter, the conical flask, drops, 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 falling. And this is the distilled liquid. So the process is same. Okay, but the difference is this column. So what does this column is for? Why it is used? Okay, let us come to that. Actually, when we use this column, it is filled with either multiple what should I say? It forms a multiple fraction. Okay, it forms a multiple fraction through which our vapors are rising up. Okay, our vapors are rising up. Now, this fractionating column is called theoretical plate. It is called theoretical plate, and it is a very important commercial method. What is the purpose? It gives several, what should I say, interfaces. It gives several places, several columns, several sites for heat exchange. Heat exchange to what? Say both the liquids are having similar or close boiling point. So when I'll start heating, they both will start rising. Okay, but definitely there is some difference. If they are exactly same, then we would have not used, but they both started rising. As they have to go through a particular column, what happens that while they are passing through these columns, they exchange their heat, they lose their heat. So what happens? The one which had higher boiling point, okay, the one which will have higher boiling point. See, when I was boiling, if one was boiling at 50, other was boiling at 60 degrees centigrade. So when I started boiling, first 50 degrees centigrade a liquid will move to gaseous phase first. Second, 60 degree liquid B, 60 degrees centigrade boiling point liquid B will move to gaseous phase. But when I'm talking about condensation, when you are cooling, it is a reverse process. From hot to cool, you are coming down. So something that needed to be 60 degree when to maintain its vapor state will cool first. So cooling first is of B, that is higher boiling liquid. Higher boiling liquid started condensing first. This is a question. This is an important point. Second cooling will be of A, जो 50 degree पर boil off हुआ. Because when you are going from down to up, you will cross 50 first, then you'll move to 60. But you are coming from upper to down, then you'll cross 60 first, and then you'll reach to 50. Okay, so what will happen when we'll go like this, right? The one which is having a higher boiling point will lose its heat and will start forming a condensate. Let us assume that red is low boiling and black is high boiling. Okay, so what will happen? High boiling, so gradually here black will come down. I would not say red is coming zero. Uska component less hota jayega. It will be less. As and as I will move up in this column, this whole thing at the top will be low boiling liquid. Because high boiling liquid on the way to top went on condensing. It went on condensing and on reaching the top, the vapors become pure. Pure in what? In low boiling component. Then we pass these vapors through this condensate. So what we get here is a low boiling point liquid out of the mixture. This is a question that in fractional distillation, which is obtained in the condensate. It is the low boiling point liquid. Okay, there could be different shapes and appearances and arrangements of these fractions, these columns. Okay, there could be different arrangements. For example, see, glass beads are set, plates are arranged, theoretical plates I just said, bubble plate column, simple pack column. And what I'm saying is not just in paper. As I said, this is a very important application. You might have came across of this big size appearances looking like a rocket or something. These are the typical industrial distillation towers. This is how they arrange. See, distillation towers. So big, so long. Okay. Inside these, the condensers and the arrangement, see the plates. Distillation columns. That is how they work inside. See one more example. This is a vacuum distillation column, industrial. So what we are drawing on paper has this level of industrial application. I hope you might be now better in what I'm saying. In fractional distillation, you can separate completely only the ideal solutions, not the azeotropes. I hope you know the azeotropes, that is the constant boiling liquids. Azeotropes cannot be separated by fractional distillations. For example, here I say, which of the following binary mixtures of miscible liquids, that is they are miscible in each other, the compounds can be subjected to complete separation. Okay, answer is A, B, D, because C forms azeotrope. A, B, D form ideal solutions. Okay, azeotropes cannot be separated because even in vapor state, they will not form a different composition. They will continue to have the same composition. So we cannot use azeotropes in fractional distillation. Okay, we can use fractional distillation for, say, methanol propanone combinations, for benzene toluene combination, and the others I just told, say chlorobenzene, bromobenzene, and all these. That is okay. But you cannot use for chloroform in this. They have a negative deviation. Okay. So today we are ending our topic at fractional distillation. Tomorrow we'll start with distillation under reduced pressure and steam distillation. So let's stop here. Today we have run a little late because of some technical issues. Anyways, please revise the lecture. Go through these all topics. Read NCERT compulsory. Okay. Then you will find some comfort in all these concepts. Tomorrow we'll complete distillation. We'll revise or we'll go for some chromatography study. And then we'll go for analysis, qualitative analysis, quantitative analysis of organic compounds. So till then,